Hello student, the question says a short bar magnet placed in a horizontal plane has its axis aligned along the magnetic north-south direction. Null points are found on the axis of the magnet at 14 centimeter from the center of the magnet. The Earth's magnetic field at a place is 0.36 G and the angle of dip is 0. What is the total magnetic field on the normal bisector of the magnet at the same distance as the null point from the center of the magnet? At null points, the magnetic field due to the magnet is equal and opposite to the horizontal component of Earth's magnetic field. So I will give a detailed explanation for this. So this video is slightly going to be lengthy. First, you should understand what does he mean by the Earth's magnetic field. So if you consider Earth, and in Earth we have geographic north, which we generally call it as north in our day-to-day life, and geographic south, and we have east and west direction. And our Earth itself would behave like a giant magnet. That means you can consider inside our Earth itself, we have a very, very big magnet. But this big magnet is not exactly aligning with the Earth's geographic north and geographic south. This big magnet is slightly at an angle with it. And one more important thing is that we have something called on a magnet also, we have something called magnetic south and magnetic north, which we are calling it as south pole and north pole. Don't be confused with geographic north, geographic south. The day-to-day life east, west, north, south that we point on maps is completely different from magnetic north and magnetic south. There is a connection between them. If I start explaining it, this video will be lengthy. Just remember that our Earth's magnetic south will be at closer to the geographic north, and our Earth's magnetic north would be closer to the geographic south, but they are not exactly overlapping. And we know the magnetic field lines will be from north to south outside. So inside the magnet, the direction of magnetic field lines are from south to north, but outside the magnet, the direction of magnetic field lines are from magnetic south to magnetic north in this way. And similarly, like if I draw one more field line, so we have to draw a complete loop in this way. So this is how the magnetic field lines exist. So rather than drawing this big diagram, next time onwards, I will represent the Earth's magnetic field just with a very giant magnetic moment. We know magnetic dipole moment concept. Instead of drawing a magnet, what we will do is we will draw an arrow. And in this arrow, the head represents magnetic north and the tail represents magnetic south. So rather than drawing all this, we can draw a Earth like a giant magnet of magnetic dipole moment from magnetic south to magnetic north. And what will be the direction of magnetic field lines? The direction of magnetic field lines outside would be in this way, from magnetic north to magnetic south. So because of this, there will be magnetic field everywhere on the Earth. So let us take this location only right now where you are sitting. If you can actually see, there will be magnetic field lines flowing, and they will be flowing from magnetic south to magnetic north. But if you can't understand all this, you can think roughly they will be flowing towards the north direction, whichever is the north direction in your room. It will be slowly flowing almost towards the north direction. You can think in that way rather than all these geographic north and geographic south. So if you can see magnetic field lines right now with your eyes, so the magnetic field lines will be going towards the north direction. And there is one more word used called angle of dip. Right now, this concept also is deleted for us. If you can actually see these magnetic field lines will not appear flat to the parallel to the floor. What do you mean by parallel to the floor? Here I have to discuss a slightly deviate and discuss one more concept, directions. When we say people east, west, north, south direction, we generally represent east, west, north, south direction in this way. We call this east, we call this west, we call this north, and we call this south. Due to this, what happened is that when somebody points their finger upward, and they says what is the direction, they generally tell it as north direction. But north direction is not upward. Remember that east, west, north, south are actually around you, they are not above you. So east, west, north, south are actually around you. Then if you point your finger upward, that is actually upward direction, and if you point your finger downward, it will be downward direction. That means you, if you keep on traveling upward, you will leave the earth, you will not go to the north pole, you will actually leave there. So a right way to look at a map is by placing it on the table. You should not look at a map in a vertical way, you should place it on the table and then you have to look at the map. So remember this. So east, west, north, south directions are around you, not above you. And when I say magnetic field lines are going towards almost going towards the north, okay, let us assume they are almost going towards the north. If you can see with your eyes, you will notice that the magnetic field lines are not exactly horizontal with the north one. They will be at some angle. Right now, why do we get that angle and all those we won't tell. That angle is basically called as angle of dip, and whatever is the earth's magnetic field is there, we have to divide again that into two components. We have to call it as b cos theta, and we have to write it as b sin theta, and then we solve these problems. But since angle of dip and all these related concepts are recently deleted from the syllabus, the only thing you have to understand is that you have a room where you can actually see Earth's magnetic field lines. Let us assume these are the Earth's magnetic field lines that are spread over your room. And since angle of dip is zero, they are perfectly parallel to the floor. They are perfectly parallel to the floor. So this is how you have magnetic field lines. Now you have a small tiny magnet with you. He has given in the question clear words. He has used the word short magnet. So imagine you have a very short magnet with you. I'm drawing it a little bit large so that it will you can visually understand. But technically, when I say short magnet, I have to draw a very, very, very tiny arrow, which you may not be able to see it also. So let me draw this and assume that this is a short arrow. So once we have our magnet in this way, why I drawn in this way? Usually, if you hang a magnet, it will align itself with the Earth's magnetic field. But in the question, it is given that our magnet is opposite to the direction. At the end, if you see at the field due to the magnet is equal and opposite to the component of Earth's magnetic field. Now again, I will slightly explain you regarding the magnetic field created by a tiny magnet. If you want to know the magnetic field created by a short magnet, so magnetic field due to short bar magnet. And what is the meaning of a short bar magnet? The size of the magnet must be very small compared to the point where we are trying to find the magnetic field. So if you take a very short bar magnet, and if you want magnetic field on the axis of the bar magnet, so this is called the axis of the bar magnet, the direction of field will be exactly similar to the direction of bar magnet. The bar magnet is pointing in this way, right? So on the axis also, anywhere, if you try to find magnetic field, it will be pointing in the same direction. On this side also, it will be pointing in the same direction. So on the axis, the magnetic field direction is similar to direction of dipole moment. In NCERT, it is indicated with small m. So I'll indicate with small m. So it is similar to the magnetic dipole moment. What is the magnetic dipole moment? It is simply take the south pole and north pole and you just connect it. That's the direction of magnetic dipole moment. Then what is the magnitude of this? For magnitude, we measure from the center of the magnet. From the center of the magnet, let us say at a distance x, you want magnetic field here. If you want magnetic field here at this point, the formula for magnetic field on the axis of this will be mu naught by 4 pi into 2m divided by x cube, where m is the magnetic dipole moment, x is the distance, and mu naught by 4 pi. So this is the magnitude and this is the direction. And this is called as magnetic field on the axis of a short bar magnet. Now let us see what is a magnetic field on equatorial line. Magnetic field on equatorial line. Suppose if I consider a bar magnet in this way, what is the meaning of an equatorial line? Equatorial line is you have to just draw a perpendicular bisector. That means at an angle 90 degree and exactly passing through the center of this. This is basically called what we call it as equatorial line. And if you try to find magnetic field at any location on the equatorial line due to a short bar magnet, the magnetic field direction would be exactly opposite to this direction. That means this is the magnetic field direction created by this bar magnet. So we can simply write the direction of magnetic field lines at equatorial point would be opposite to the direction of magnetic dipole moment. And one more thing, what is the value of this? The magnetic field value at the equatorial point would be mu naught by 4 pi into m by r cube. If you notice it, it is 2m by x cube, x or r, where x and r anyway both of them represent distance only. So if you notice it, magnetic field at the equatorial magnitude is half of magnetic field on the axial line, because in the axial line the formula is 2m by x cube. Here we are getting just m by x cube. And one more, the direction of the equatorial line is simply opposite to the direction on the axial point. I hope these terminologies, these formulas are pretty clear. Now we will use this entire thing to solve our problem. So let us look at the problem now. So this is the problem that is given. A short bar magnet is placed in a horizontal plane with its axis aligned along the magnetic north. Null point is found at an axis of magnet at 14 centimeter from the bar magnet. Suppose if you take our bar magnet as in this way, and since magnetic field lines of the earth are continuously going in opposite direction at every point, like in the entire room, the magnetic field lines are continuously traveling in opposite direction. You select one point on the axial line. So you select one point. Let us assume that point is at a distance a from here. And the magnetic field due to our magnet, the magnetic field would be in this direction. And magnetic field due to the earth, we can clearly see it is in opposite direction. So here at null point, what happens is that, let me call this point. So at null point, both the forces would balance each other. That means magnetic field due to magnet, that is short bar magnet, is exactly balancing magnetic field due to the earth. So I'll call this as BE. And it is given as 0.36 G. So indirectly we can tell, we know at an axial line, the formula is mu naught by 4 pi 2m by a cube is equals to magnetic field on the earth at that location. Whatever is the location, that location A value is also given as 14 centimeter. Now the question says, what is the total magnetic field on the normal bisector of the magnet at the same distance from the center of the magnet? Now, if this is the situation, he is asking you take the same magnet on the normal bisector. So if this is my normal bisector, at the same distance from it, consider same distance A, is asking what is the magnetic field at a new point. So at the new point, due to the bar magnet, what will be the direction of magnetic field? The direction of magnetic field due to the bar magnet would be in this way. And we know Earth's magnetic field is continuously flowing in this direction only, right? So Earth's magnetic field anyway will always be in the same direction, just because we are finding at the null at some other point, it's not like Earth's magnetic field would change. So it is constantly pointed in this way only. So based on that logic, I can draw Earth's magnetic field at this location in the same direction as the magnetic field due to a bar magnet. So this is due to our magnet and this is due to Earth. So we can clearly see the net magnetic field would be, both are pointing in the same direction. So magnetic field at the equatorial point plus magnetic field due to the Earth. We know magnetic field at equatorial point for same distance A. That is very important. He has used the word same distance as the null point. So it would be half of magnetic field of the axial point plus magnetic field due to Earth. So simply, we know magnetic field due to an axial point at a distance A is exactly equal to magnetic field due to Earth. So we can write half B Earth plus B Earth. So we ultimately get it as 3 by 2 B Earth. So finally, we got the conclusion for this is that he's asking you what is the total magnetic field on the normal bisector of the magnet at the same distance as the null point from the magnet. You can see all these numbers are given, but we have not used any of those numbers. So directly we can tell the answer would be, so B at normal bisector point, normal bisector point would be equals to 3 by 2 B of Earth. And B of Earth is given as 0.36 Gauss. Again, he has used the word Gauss. What is this? 0.36 into G. Remember, 1 Gauss means 10 power minus 4 Tesla, which is SI unit. So 3 into 0.18 into 10 power minus 4. 0.18 into 3 is 0.54 into 10 power minus 4 Tesla. So you will get 5.4 or 54 into 10 power minus 6 Tesla. So this is the overall concept of the given problem, and this is how we are supposed to solve it. So remember, if you know all these things, like whatever I explained, how, what do you mean by Earth magnet, what do you mean by dip, and what do you mean by the poles, and all those things, we can directly solve it in a single go. Like initially, as soon as we read that there is a null point at this distance, so that means B Earth is equals to B of the magnet, and we want on the normal bisector, so it will be B by 2 plus BE, so 3 by 2 BE. We can do it in a single step, but I wanted to explain the entire concept in detail. Hope you understood how I have solved. Thank you.